Good evening. I'm Kristen Dyer, Director of Alumni Relations, and I'd like to thank you for joining us for Alumni Education's Learning Chemistry Through Lab Demonstrations. This live lecture, presented for Holy Cross alumni and friends, will be given by chemistry professor and class dean, Ron Jarrett. Professor Jarrett holds a PhD from Yale University and is a past recipient of the Holy Cross Distinguished Teaching Award. You can submit questions to Professor Jarrett at any time during the lecture by using the chat function on the right-hand side of your screen. You can also submit questions via Facebook, Twitter, or email. At the end of the presentation, Professor Jarrett will take a selection of questions on the related topic as time allows. Thank you for joining us. And now, Professor Jarrett.
Thank you, Kristen. I've had the pleasure of being a Holy Cross faculty member for the past 24 years, half of that time as department chair, and the last 2 years as class dean for the class of 2012. The chemistry department here has a vibrant research program, and about 20 years ago we decided to develop a method in our chemistry courses to reflect that same scientific process. So our courses still have a traditional content. They still blend lecture and lab, but where we differ is that we use the lab to actually drive the course. It helps bring the students in as more active participants in the learning process, and by having the lab drive the discussions, we use their actual data to cover otherwise traditional topics. So most of our discussions start with an observation or a question, and then a hypothesis is drawn. We test that hypothesis in the lab, and what typically happens is that students are each running a slightly different experiment in the lab so they can answer a question with their own results, but then much more powerful to pool the data and draw a larger relationship for the particular topic that we're studying. We're coming to you from the Organic Chemistry Lab, which is part of the New Science Complex, and my specialty is organic chemistry, which is sandwiched in between Gen Chem 1 and 2, atoms and molecules, and equilibrium and reactivity here at Holy Cross. So not only do we use the lab differently in terms of our courses, our sequence is a little bit unique. I mentioned that we start our discussions with an observation or a question, and really what I'd like to do for you is just go over some of the demonstrations that I've used from time to time to spur a discussion. I've tried to have a common theme going on here that is looking at properties of gases and the relationship of pressure volume of those gases and temperature. You'll notice I have many things up here in duplicate. That's because if the conditions aren't quite right, I'm afraid the demonstrations might fail. But hopefully we'll get some of them to work on cue in this live broadcast. So you get the gist of what it is that we try to do here. The first thing I'd like to start with is using carbon dioxide. I'm sure everybody's familiar with that. You're probably more familiar with it in its gaseous form, but I'm going to use a bit of it here as a solid, also known as dry ice. And the interesting thing about carbon dioxide is it goes straight from the solid to the gaseous form, hence the name dry ice, as opposed to going through a liquid. So if I put that solid into the balloon and allow the solid to warm up, we should see the effect on the corresponding gas. Get a little bit more in there and see if we can't get the balloon to inflate accordingly. And it's giving me a little bit of it. Freezing the rubber of the balloon, making it difficult to put it in. We'll try that again. One more try. Different balloon. That should be enough to make the point, seal up the balloon, and see if we can't coax the solid to go into the gas phase and fill up the balloon. Okay. Now the question would then be, what would you expect would happen if I cool it back down? I think everyone would agree we'd expect the balloon to decrease in volume, but the question would be, to what extent? Do you expect it to collapse entirely, only partially? In order to test that, we'd need to expose it to conditions that are colder than at least room temperature, or ideally even colder than the dry ice block. And to do that, I'm going to use some liquid nitrogen. And again, I'm sure you're familiar with this. Many a villain have, in the movies, met their demise by falling into liquid nitrogen and instantly freezing. So if we take that balloon and cool it down, you can see it's starting to collapse and has done so entirely. Okay. Now, the question that we might want to ask is, did it collapse entirely because all gases would collapse entirely at this temperature, or is it somehow related to the special property of carbon dioxide that takes it from the gas form and brings it back to the solid? In other words, is it just a function of the temperature, or have we effectively not only changed the temperature, but decreased the amount of gas that was present? So to answer that, we would have to try other gases. And that's what I was referring to before, trying little variations on a particular example. These balloons have been filled with helium and nitrogen. And if I try to do the same experiment, where I'm just applying a little pressure on the balloon to try and put it in the liquid nitrogen, you can see that it is not collapsing. It's a little difficult to tell, but that sound you hear is because, and maybe you can pick it up visually, because the balloon is collapsing a little bit, but not entirely. So there is a correlation, there's a connection between pressure, volume, and temperature, but it's not as dramatic as the carbon dioxide would have led us to believe. Okay? So we do have that relationship. It quickly reinflates. That's fine for balloons. Can we do anything a little more substantial in terms of seeing that same effect? And what I'd like to try, and this one is a little more finicky than some of the others, is to see if we can do the same type of cooling down and collapsing using a soda can instead of a simple balloon. So all I've done here is to put a little bit of water into these soda cans and heat them up so that there is steam, gaseous water that's filling the can. And what I want to do is quickly invert it into a beaker of water to see if the rapid decrease in temperature of that vapor will allow for a visual effect on the can. Well, let's give one a try and see what happens. Oh, right off the bat. So I always jump a little on that one. As I think you can see, the reduction of the gas in the can, once I've sealed it by putting it bottom first into the water, has created a vacuum that has sucked in the sides of the can, similar to what we had seen decreasing the temperature on the balloon. As we try to think about again in terms of what could be done in terms of being a bit more dramatic, what we would try to do is create a situation where we have a more rapid expansion or contraction of the gas. And to help me out with that one, I've got some homemade cork guns over here. And all I've done is to take a plastic bottle, 2 nails that are inserted that are just separated by 1/4 of an inch or so, and my projectile is a cork. And what I need is some fuel that I'll be able to rapidly turn into a gas. So I would use a little ethanol as my fuel. And just going to take a minute to make sure that I can fill the bottle as much as possible with the ethanol. And essentially what I want to do is burn it and turn the ethanol into carbon dioxide again and water as the combustion products from that, but they would be in the gas phase. And if they're created with sufficient force, if those gases are created with sufficient force, then they ought to be able to launch the cork. And again, I've got a couple of these in case we don't have things quite right. But what I'm going to do to try and ignite those gases, the ethanol to create the gases, is to use a Tesla coil, which will shoot out a little spark of electricity and hopefully jump to the other nail, launch the cork. All right? So why don't we see if we can get this to work without shutting down the equipment. There we go. Oh, that was a good one. Never lost the cork in all the years of doing this. So what we have is the generation of the carbon dioxide and water, as I say, through combustion. It's a little tough to see the combustion through this opaque material. I do have another bottle, clear, and if we do the same thing, we ought to be able to get a better look at the combustion that's going on to illustrate that creation of gas and the pressure that launched the cork. I think for a better visual, we're going to shut off the lights in a moment so you can focus right on the flame that should be in the bottle. And cork. Is that a good spot? Okay. You can go ahead. Here we go. Whoops. Oh, there we go. And a nice bit of flame that came out of that. Not quite the 1.21 gigawatts that you need for most science experiments, but it did the job. As I say, created the gas at high temperature, expanding. And if we really want to see that gas taken at high temperature and expanding, we can go one step further and explode some balloons of flammable gas. All right? So the next item that we'll take a look at, I'm trying to remember why I color-coded them, but the next ones that we'll take a look at would be balloons of hydrogen gas. Making the balloon float. It's just hydrogen gas that's been placed in here. And when I put a match to it, we ought to see the combustion of the hydrogen and the energy that's released accordingly. So to do that, I'm going to take a few safety precautions, although for this particular one it shouldn't be necessary. But I am going to try to be safe here. So I am going to cover my ears as we get ready to ignite the balloon. Doesn't hurt to stand back a little either. There we go. Not bad. We can, being chemists, we like to try and make things more efficient, and we can increase the efficiency of that combustion if we increase the content of oxygen that's available. And again, I sort of eyeballed these, and there are a couple of different proportions of the oxygen and hydrogen in this one. Because of the extra oxygen, the balloon at this point of the time of the day isn't floating anymore, but it's standing upright. It still has plenty of hydrogen in it. And the prediction should be the greater efficiency, the greater release of energy all at once should create a larger shock wave, and it should come out louder. So let's see if indeed that is the case. Here we go. My camera crew is safely protected. Seemed a little louder to me. And the last thing, I have one more small demonstration to do for you, and it's sort of to round out the series. We started by looking at creating a gas by changing its phase, going from a solid to the gas form with the carbon dioxide and the water, where we went from the gas to the liquid. And then we looked at creating gases through chemical reactions, combustion, where we ignited a liquid, the ethanol, and created the gases that way. We ignited a gas, hydrogen, to create more gas. We've done it that way. And the last thing I was going to do for you, again, just really for completeness, would be to create a gas from a solid. And what I'm actually going to be doing is an acid-base reaction. I have a solution here. It's an acidic solution. And I've got a solid here. Misplaced my funnel. And I'm putting the solid into the balloon just so I can add it into the solution. And if I am successful generating gas, then the balloon will capture it. The solid that I'm putting into the balloon is a household item. It's sodium bicarbonate, baking soda. And for those science fair enthusiasts who have made volcanoes at home by taking baking soda and vinegar, it is essentially the same kind of thing that I'm doing here. That should be enough for our purposes. Just attach it here. And we'll add a little in. See some fizzing taking place. Generating the carbon dioxide and filling the balloon. At least I'm proposing it's carbon dioxide. Had we used a different solid with this same acid solution, it could have been hydrogen gas that we were generating. And we've seen different behaviors of the carbon dioxide and of the hydrogen. So to test my hypothesis that this is carbon dioxide that I've generated and captured, it should behave the same way as our original carbon dioxide balloon had when I submerge it back into the liquid nitrogen. That is, it should collapse entirely instead of just partially. So to bring this full circle, we'll go back to the liquid nitrogen. take this balloon, apply a little pressure, see if we can't get it to collapse entirely. Which we have done. Okay. Confirming the idea that it was carbon dioxide that I was creating. Obviously, we could do additional tests for further confirmation. I hope through these series of demonstrations I've given you the idea that we really do want to use a hands-on approach here in the way we teach and learn chemistry, that we actually take our sciences very seriously here, but that doesn't mean we can't have fun along the way. So with that, if there are questions, I would be happy to take them. Why? Okay, so our first question is regarding the pop gun. Why did I have to roll the methanol around? I wanted to make sure that the methanol was coating everything in there, so when the spark jumps across from nail to nail, it encounters ethanol that it can then ignite and get the process going. Each of these demonstrations are ideas that have come up over time where we try to think of ways that would make an impression on a student when we're trying to discover a topic. If you remember your high school chemistry, if you've gotten there, you're probably familiar with the expression PV equals nRT. Pressure volume equals amount of gas times a constant times temperature. And that's really what is the foundation of all of this. And rather than starting with that equation and going on from there, we try to do it in a way where we make observations and see what's there. But we've had to hone these demonstrations so that they make that impression and also follow the laws in the chemistry that we're trying to discuss. We have another. What type of material is the bottle wouldn't melt under high temperature? I have to confess that if I put too much ethanol in, I have melted these. These are really just plastic. And the reason they don't melt is the flame burns so quickly that it just doesn't have enough time and at that elevated temperature to actually melt the plastic. But it would melt under the right conditions if that's what you were trying to achieve. What was in the second balloon and why did it react differently than carbon dioxide? These other balloons are different gases. The green is nitrogen, like most of the air you're breathing, 80% of the air you're breathing. And the purple is helium. I didn't put very much in because I wanted it to be able to fit in the dewar, so that's why it's not floating off on its own. But those are the gases that are common, that we have available to us here in the department. And the reason it didn't behave as the same as the carbon dioxide is because it has different physical properties. The same way why ice floats when it goes into a solid, whereas most compounds are more dense in their solid phase and would sink. So various compounds do have different physical properties that lend to their behavior. The phase diagrams and phase relationships of many common compounds have been studied, measured carefully, and graphed so that we can see how their behavior will occur at various pressures and temperatures. So it's just the properties, the behavior of the different gas. And when you think about that equation, PV equals nRT, it's for these types of gases that equation makes sense because we're not changing the amount of material that's in the balloon. It's the same amount of gas is present at room temperature as well as sitting in this dewar. That's not true for carbon dioxide. For carbon dioxide, as we change the temperature, some of the gas goes to solid and we don't have the same amount of gas in the balloon, and that's why the effect is more dramatic where it collapses entirely. Let me see if we have another. Does the CO2 gas become liquid in the liquid nitrogen, or is it directly solid? Directly solid, and I think we can sacrifice a balloon. I'll rip it open and dump it out. These are all good questions. These are the types of things that we would be doing in the class in terms of spirited discussion and developing a hypothesis, doing some kind of experiment to test that hypothesis, refining our prediction if need be, and going on from there. See if I can just break it open. Probably not. Oh, yeah, I did. No liquid. You can see it's the solid coming back out again. And again, other than a little condensation of water from the air that might happen, this is just going to evaporate away and not make a mess. So that will be convenient as well. Can you do the balloon explosion with the lights off? I'm game. We've got them here. We'll do, is it easier to do the pure hydrogen, the quieter one, with the lights off? Don't think of that. So why don't we do that one? So everybody has a fix on the approximate location of the balloon? We're okay? Here we go. That's a nice one. The only other thing I would end with, in terms of if you have questions about our chemistry program, our research program, or even as class dean, I'm happy to address any questions that you might have. Seems like we have another. Now that the new labs are up and running, if the Holy Cross Chemistry Department has a wish list, what items are on it? We would be greedy if at this point we asked for anything more. This organic lab has hood space for 32 students in it, and if you hear any noise at all, it's coming from the ice machine. So this is a wonderful facility for teaching and learning chemistry. There's a counterpart for general chemistry on the other side of the wall. We have a discussion and work area dedicated to the lab just outside here. There's instrumentation on the center benches. It's actually decadent in terms of how many GC mass specs we have here running for a single experiment, as well as the FTIRs. Our research facilities are spacious, well equipped. The instrumentation that we need is maintained and going. And quite honestly, years of planning actually went in to the construction of the facilities and equipping it, so that at this stage we are all in excellent, excellent shape in terms of doing our research, which is student-centered, by the way, and teaching and learning chemistry in our labs. Our lecture halls are on the floor below, where, again, close proximity so we can make the transition between lecture and lab with great fluidity. Please be careful.
Thank you to Professor Jarrett for sharing his time and knowledge with us tonight. We'd like to invite you to continue the conversation on the Holy Cross Alumni Facebook page. Just search Holy Cross Alumni and you will find tonight's lecture as one of our topics. Thank you so much for joining us. Good night.
Thank you very much.